Greetings, folks. Welcome. There are lots of applications of regression analysis where we want to look at the relationship between a dependent variable and more than one explanatory variable. So here you see a generic regression model where y equals beta subscript 0 plus beta subscript 1 times x1, that's the first explanatory variable, plus beta 2 times x2, where x2 is the second explanatory variable, all the way out to beta subscript k times xk. So we're assuming here that there are k explanatory variables. That could be 4, 5, 6, whatever that number might be, plus epsilon, which is an error term, because even though we have more than one explanatory variable in the model, there are still other factors that we're not controlling for that might have an impact on the dependent variable. Here's a multiple regression model where we're trying to look at the keys to getting a good grade on a test. So the dependent variable is your grade. That's equal to beta naught plus beta 1 times how much you study, plus beta 2 times how much sleep you got the night before the test, plus beta 3 times your GPA, plus beta 4, that's your attendance in the class, plus epsilon. In this regression model, k equals 4 because we have 4 explanatory variables, and we're trying to look at the effects of studying, sleep, GPA, and attendance on your test grade. A nice feature of multiple regression model is that regression results control for all the variables that are included in the model. So for example, the value of beta 2 is interpreted as the effect of the amount of sleep that you got on a test grade, but we're holding constant a student's studying, GPA, and their attendance. We often use the results from a multiple regression model to do a hypothesis test. So as an example, I have this idea that I think that attendance has an impact on a student's test score. So let's go through the 5 steps of the hypothesis test. The first step is to write out your hypotheses. Of course, the alternative hypothesis is your claim. So here the alternative hypothesis, H subscript A, is beta 4 is not equal to 0. So of course, the null hypothesis is that your claim isn't correct. So we can write out the null hypothesis as H subscript 0, beta 4 is equal to 0. The second step of a hypothesis test is setting the significance level. In this example, I'm using a 1% significance level. So that means there's a 1% chance that I'm going to make a type 1 error of rejecting the null hypothesis when in fact it's true. In other words, I would falsely find support for my claim. The third step of a hypothesis test is calculating the test statistic. So here you see the test statistic T equals B subscript 4 hat. This is the value from your research telling you the effect that attendance has on your test score, minus beta 4 naught. This is the value from the null hypothesis, divided by the standard error of the sampling distribution of B4 hat. So let's say I collected data on 40 students, and I ran a regression or estimated some regression results, and found a value for B4 hat as 1.420. That would be interpreted as, for every additional day of attendance, your test score might go up by 1.42 percentage points. You subtract from that the value from the null hypothesis, which was 0. Divide that by the standard error of the sampling distribution. And let's say from my research that was 0.71. This would give me a test statistic of T equals 2. And you could interpret this as the value from my research is 2 standard errors greater than the value from the null hypothesis. Because the test statistic follows the t-distribution, we have to think about the number of degrees of freedom, and that's calculated as n, which is a sample size, minus k, that's the number of explanatory variables in the regression model, minus 1. There were 4 explanatory variables in the model, so 40 minus 4 minus 1 gives us 35 degrees of freedom. To calculate the p-value, we have to start by finding the area of the t-distribution that's to the right of a t-value of 2.0 in a distribution with 35 degrees of freedom. So I sketched out a t-distribution with 35 degrees of freedom, and you can see a line that corresponds with t equals to 2. So we're trying to find the area under the curve to the right of that line. So we'll go to our t-distribution table, which shows us the area under the curve in the upper tail. Let's go down to 35 degrees of freedom, and we're looking for a value of 2. So if you go across that row, you see 0.852, 1.306, 1.690, 2.030, and then 2.438, and finally 2.724. Again, we don't find a value of t equals 2, so really all we can say is that the area in the upper tail of the distribution with 35 degrees of freedom and t equals 2 is between 2.5% and 5%. So we can actually go back to our t distribution with 35 degrees of freedom and write in that between 2.5% and 5% of the distribution is greater than a t-score of 2. So to ultimately calculate the p-value, you have to bear in mind that this is a two-sided hypothesis test. So therefore, we have to multiply that area in the upper tail, which is between 2.5% and 5% by 2, which gives us a value of between 5% and 10%. So this p-value means that there's between a 5 and 10% chance that if the null hypothesis is true, in other words, if beta 4 is equal to 0, you could get a value that is more extreme than the test statistic of 2 that we found from our sample. The fifth and final step of the hypothesis test is to compare the p-value we just found to alpha. So in the second step, we set an alpha of 0.01, which meant that we're willing to tolerate a 1% chance of rejecting the null hypothesis when it's true. Now, after doing our research and calculating our p-value between 0.05 and 0.1, we've now learned that there's between a 5 and 10% chance that if the null was true, we could get a test statistic of 2 or higher. And because this p-value is greater than alpha, we cannot reject the null hypothesis in favor of our claim. In other words, we cannot say that with a 1% significance and based on our sample of 40 people, that attendance impacts your test grade. In other words, there was not strong evidence suggesting that the number of times you go to class has an impact on your test score.